Before we talk specifically about circular motion and some more complex questions, let's remember how we dealt with net force in a previous section. So in this first situation, we have a block that's sitting on the floor. I put it inside of a box because later on it might be helpful to think of this as an elevator. So if you have something that's sitting on a floor and there's no acceleration, to consider the forces that are acting, there would need to be gravity pulling down, which you can label as F sub g, or you may just want to label it as m little g right away, just to help you remember that that's the formula you're going to be using to calculate the weight. And then because there is no acceleration, there has to be some sort of upward force balancing. And in this case, because it's a floor in contact with it, a surface, it would have to be a normal force. And those two forces would be equal and opposite to each other. If we wrote out what F equals ma is equal to, we would notice that they subtract to give us 0, or that F sub n would equal mg. But if our box is accelerating with this mass inside, and it's accelerating upward, then although there is still that same amount of gravity pulling down, there would need to be a larger force upwards. If the acceleration is upwards, then the net force must also point upwards. And so the normal force would need to be bigger in this situation. If we wanted to figure out what the value of acceleration was, and we needed the net force, we might decide to either take normal force minus mg or mg minus normal force. And the way we choose is that the net force direction is our positive direction. And so in this case, that would be F sub n minus mg. Now in this other case, if it's accelerating downward, we could stick with up as our positive direction. But a lot of times what we'll do is take the direction of acceleration to be the positive direction. We've done that before. And that's going to be the general rule we'll use for circular motion as well. So we still have that same gravitational force pulling down, but because the object accelerates downward, the net force has to be downward as well. So the down force has to be bigger than the up force. Our normal force would need to be a little bit smaller in this case. And if we were going to set up our equation, rather than doing it the way we did it over here, F sub n minus mg, because the acceleration points down, we're going to go ahead and have that downward direction be the positive direction. This is going to set us up for our circular motion problems here in a few minutes. So in this case, we would want to say that mg minus F sub n is equal to ma. That way, the direction of the net force matches the direction of the acceleration. So what if our elevator is not an elevator? What if our object is actually moving around in a circle? Now you might wonder, well, where would we see that sort of situation? Well, a snowboarder, for instance, on a half pipe. As the snowboarder goes down one side and then comes up the other side, that is going to be a curved path. And at the bottom, where this star is, this situation is represented in the diagram. Or on a roller coaster, as the cart travels through a valley of the roller coaster, at that bottommost point, this is sort of the situation that we're looking at. And that's what we're going to focus on for right now. We're going to think of this as part of circular motion, and so we need to think about the direction of the acceleration. Recall that with circular motion, the acceleration always points inward. And so in this case, if the mass happens to be at the bottom of the circular path, then the direction of the acceleration would be upward. Again, always pointing towards the center. That's important to recognize right away because that means the net force will also point upward. Our forces are not going to point with the motion. They are going to point perpendicular to the motion. So if we were going to write our F equals ma, we're going to need to know our forces. Again, gravity is always there, always pulling downward on our object. And in this case, there would have to be, again, a normal force. And the normal force would have to be bigger than gravity so that the net force points in the upward direction. Putting that into our formula, it looks similar to what we had before with like an elevator that's accelerating upward. It's just that in this case, this acceleration is not with the motion. The acceleration is a centripetal acceleration that's causing the object to rotate. So again, notice the key ideas here is we needed to know what the forces were and which way they were pointing. We needed to know which direction the acceleration pointed, which way inward was. And that direction is where we begin our formula. We start with the same force that points in that direction as we write the net force. Let's look at another situation. So here we have an object that is on the top of the circular path. Again, some examples of where you might see that. On a roller coaster, this would be going over the top of a hill, or on a Ferris wheel. Okay, these are all situations where you have an object that is sitting on something. Now, the Ferris wheel kind of looks like it's suspended, and if we were thinking about the car itself, that might be different. But I'm thinking about the person inside, and the person inside is sitting on a chair, and that person's going to be supported upwards by a normal force, just like the people in this roller coaster are supported upward by a normal force. So if the block is on the top, or the object is at the top of the circle, inward now means down. So again, our discussions earlier about which direction does acceleration point, here's where that's really going to come into play. We're going to have the same forces as we did before. We're going to have gravity pointing down, and we're going to have normal force pointing up. But in this case, because the acceleration is down, the net force must be down. And so this force, this gravitational force, is going to be bigger than the normal force. And when we write our F equals ma equation, we're going to start with the force that points with the acceleration. So we're going to start with the gravitational force and subtract the normal force because they're pointing in opposite directions. And again, it doesn't mean that the object accelerates downward in that its motion is changing downwards. It means that its acceleration downward is causing circular motion. And so the centripetal acceleration formula would be used here. We would be plugging in v squared divided by r for our acceleration. All right, one more example of just kind of thinking through it, and then we'll look at an actual number problem. So sometimes roller coasters go upside down, and the people themselves are below the track. Again, notice how that's different from the other situation where the block was on top of the track. Here we have the object below the track. And what that means is that the normal force is no longer going to be up. It's going to point down because the surface is above the object. Let's look again at the forces here. They're going to be referenced in the direction of this inward acceleration. The object is at the top of the circle, so inward would mean down. We're going to have our gravitational force and our normal force. Now, look at how different this looks, though. The normal force also points down. And that, again, is because the object is no longer on top of the surface. It's below the surface. And so the surface is what determines which direction normal force points. Since the two forces point in the same direction, we don't subtract them when we find the net force. We add them together. They both contribute to the centripetal force, the net force. And so F sub n plus mg would give us our mass times our centripetal acceleration. By the way, kind of a fun physics demo that involves this is to take a bucket filled with water and swing it around. And it seems like it should be, getting this person wet, But because of the way, if you go fast enough, there is sufficient centripetal forces to keep the water moving with the bucket, and they sort of fall together, kind of like how the astronauts fall towards the Earth with the space shuttle, and so they orbit together. It's sort of the same sort of an idea. All right, let's take a look at a number problem here. Move on from this guy. So here we are in one of our situations where we have somebody going across the top of a hill, and we're given some information about speed and the height of the hill as 12 meters and a mass. Okay, so the first thing we're asked to find is the centripetal acceleration. So recall that in order to do that, we need to know the speed and we need to know the radius. One of those I don't exactly know. Hopefully you can see that in the problem. In order to find the radius, we are going to have to split that height in half. The height is from the top to the bottom of the circle, but we only want half of that to be the radius. So R is going to be 6 meters in this case. And then to calculate centripetal acceleration, it's pretty straightforward because we've been given the speed of 4.8 meters per second. So we find that our centripetal acceleration is just that speed squared over r. It comes out to be 3.84 meters per second squared. Now, knowing this value, we're going to be able to figure out the normal force, which is something that's usually that you can't like measure directly. It's usually something that you're going to have to calculate from other things. Whenever you're dealing with forces, it's a good idea to think about a force diagram if it's kind of complex and there's multiple forces acting. So we would again have our gravitational force, we always do. And then because the skier is on top of the hill will exert an upward force. And so the normal force would point up. And I've drawn this arrow to be a little bit shorter than the blue arrow because the centripetal acceleration is going to point down. It's going to point inward from the skier towards the center of the circle. And so the net force is going to have to also point in that direction. There has to be more inward force than outward force. So when we set up our F equals ma equation, we would take that inward mg force and subtract the outward F sub n force. That way our net force points in the same direction as centripetal acceleration. And notice I've also changed the a to a sub c to remind myself that I need to use v squared over r for that value, which of course we did in the first part of the problem. Let's put in some numbers that are known. So we can use 70 kilograms as the mass that was given. Our little g value is 10. Notice that we don't need to worry about the whole capital G, M1, M2, and so forth here. This is a problem that is happening near the surface of the Earth, and so we don't need to use that more formal gravity. F sub n is our unknown, and then our mass and our acceleration. Go through a little bit of algebra, and we find that the normal force is smaller than the gravitational force like we expect. And what this means is that if we were this skier sort of going over the top of the hill, we wouldn't feel our usual weight of 700 newtons. We would feel lighter than that. So the normal force gives us our impression of what our weight is. If we're standing on the ground, it's the same as our weight, and so we feel our true weight. But if something else is happening to us where there's an acceleration on our body, we can feel different than usual. We can have an apparent weight that is either greater than or less than the actual. And in this case, you would sort of feel light. You would feel like you're almost floating as you go across the top of that hill.